We were discussing natural convection in the previous lecture. When an object at a higher temperature is immersed in an ambient fluid at a lower temperature, the fluid temperature close to the object increases because of conduction from the object. As the fluid temperature close to the object increases, the density of the fluid close to the object decreases, and therefore it experiences a buoyancy force upwards, and this causes a rise of the hot fluid, and cold fluid from the ambient flows in to replace the hot fluid and gets heated and once again convects heat away, and this is called natural convection. So, we were analyzing natural convection using the Boussinesq approximation, you recall in the last lecture. The Boussinesq approximation is basically that the density variation is a linear function of the temperature variation, where this function beta is the coefficient of thermal expansion with dimensions of inverse temperature. Okay. So, in the buoyancy force alone, we include the density variation due to the temperature variation. In all the other terms in the momentum, mass and energy conservation equation, we neglect the variations in the density, the viscosity and the thermal conductivity. Okay. So, those are the Boussinesq approximations, and I had discussed the conditions under which this is valid. It is valid in gases provided the change in temperature, the difference in temperature is small compared to the ambient, the absolute temperature in Kelvin. Okay. And in liquids, when the temperature difference is too large, there is often a variation in viscosity which can be large, and then this approximation is not valid. The density specific heat can be considered a constant in most cases, but there could be variations in the thermal conductivity and the specific heat. So, using that, we had scaled the equations and got the Boussinesq equations. Okay. And these were the Boussinesq equations that we had obtained in scaled form, where the temperature is scaled by the difference between the surface temperature of the object and the ambient temperature. The velocity is scaled by a characteristic velocity, and the length scale is scaled by the characteristic length. Okay. Here there are two dimensionless parameters. One is the Prandtl number, the ratio of momentum diffusion and thermal diffusion. Okay. And the other is what is called the Grashof number, which, as I told you, is the square of a Reynolds number. Okay. The Reynolds number based upon the characteristic velocity, okay, is mu infinity by rho infinity times the characteristic velocity times the length scale. That is the inverse of the Reynolds number. The Grashof number is the square of that. The characteristic velocity, recall, was obtained by balancing the inertial force density and the gravitational force density in the momentum conservation equation. Okay, we balance the inertial force density and the gravitational force density in the momentum conservation equation to determine the magnitude of the characteristic velocity. And that characteristic velocity, if you use that in a Reynolds number, okay, if you define a Reynolds number based upon the characteristic length and the characteristic velocity, the Grashof number is the square of that, and the second dimensionless group is the Prandtl number. We had discussed when we did dimensionless groups that the Grashof number is usually very large. Okay. It is usually between 10 power 4 or higher. Okay. Grashof number is large implies the Reynolds number is large, or momentum convection is dominant compared to momentum diffusion. Similarly, when the Grashof number to the half times the Prandtl number, okay, which will be a Peckley number based upon the thermal diffusivity and the flow, characteristic flow velocity. Okay. When that is large, thermal convection is large compared to thermal diffusion over length scale comparable to the characteristic length. Okay. However, if you neglect diffusion altogether, the boundary conditions cannot be satisfied, because transport perpendicular to the surface can take place only due to diffusion. There is no convection perpendicular to the surface. Therefore, we have to include the effects of diffusion in a thin boundary layer close to the surface and determine that boundary layer thickness from the condition that the convection and diffusion are comparable in the limit as the Grashof number goes to infinity. So, we had written down the conservation equations, okay? And in this high Grashof number limit, I have to scale my cross stream coordinate, okay, because the thickness of the boundary layer is small compared to the radius of curvature of the object. I can consider, for the purpose of the boundary layer analysis, the object to be a flat surface, because the thickness of the layer is small compared to the radius of curvature, and define locally a streamwise coordinate along the surface and a cross stream coordinate perpendicular to the surface. And the cross stream coordinate is scaled by the boundary layer thickness delta star, a scaled boundary layer thickness times LC. Okay. The streamwise coordinate is scaled as usual by x star is equal to x by LC. Okay. The streamwise velocity has to be scaled by the characteristic velocity. So, I have to use Vx star is equal to Vx by Vc. Okay. The cross stream velocity will not in general be comparable to the characteristic velocity, because the velocity has to be 0 on the surface. Okay. Therefore, you would expect the cross stream velocity to be small within the boundary layer. The scaling for the cross stream velocity can be obtained from the mass conservation equation. Okay. The mass conservation equation is partial Vx by partial x plus partial Vz by partial z is equal to 0. Okay. Scaling x, Vx and z, we get Vc by Lc partial Vx star by partial x star plus 1 by delta Lc. Okay, cross stream coordinate is scaled by delta times Lc. Okay. Therefore, you can see that I have to define, for the two terms to be comparable, I have to define the cross stream velocity scaled as, okay, Vz by delta star times Vc. Okay, Vz by delta star times Vc. That is, the cross stream velocity scales as delta star times Vc. Okay, so, that is the scaling for the cross stream velocity, which emerges from the mass conservation equation. Okay, so, this is a scaling for the cross stream velocity that emerges from the mass conservation equation. Okay. Let us now turn our attention to the scaled momentum conservation equation, first in the streamwise direction. Okay. The scaled momentum conservation equation first in the streamwise direction. Okay. The momentum conservation equation is Vx partial Vx by partial x plus Vz partial Vx by partial z. Okay. This whole thing is multiplied by rho infinity, recall. There should be a t minus t infinity here. Okay. So, this is the conservation equation, and I can substitute in terms of the scaled variables here. Okay. On the left side, you can verify that you will get a factor of rho infinity Vc square by Lc, okay, into Vx partial Vx by partial x plus Vz plus partial Vx by partial z plus. Okay. I will start here, so I have enough space. I have used the same scaling rho infinity times Vc square for the dynamical pressure, okay, in this case as well. Okay. And on the right side, I will have mu infinity into Vc square, I am sorry, Vc by L square. Plus the buoyancy term rho infinity g beta into t minus t infinity t star gx star. And if I divide throughout by this prefactor here, okay, and with my definition of the characteristic velocity, okay, with my definition Vc is equal to root of g beta t minus t infinity Lc. Okay. This should be t0 minus t infinity, kindly note that correction. Okay. And this should be t0 minus t infinity times t star. Okay. T minus t infinity is t0 minus t infinity times t star. Okay. So, with this definition, okay, if I divide throughout by this, okay, these will cancel out, okay, and here I will get, okay, so that is the streamwise momentum conservation equation, okay, plus okay, the buoyancy term, okay, plus the buoyancy term. Okay. And you can see that the cross stream diffusion, the cross stream momentum diffusion term is multiplied by 1 by delta square. Okay. The cross stream momentum diffusion term is multiplied by 1 by delta square. Delta is small compared to 1 when the boundary layer thickness is small compared to the characteristic size. 1 by delta square is a large number. Okay. Therefore, the cross stream diffusion term is much larger than the streamwise diffusion term, as you would expect for any boundary layer solution. And therefore, within the boundary layer, streamwise diffusion can be neglected in comparison to the cross stream diffusion. Okay. Streamwise diffusion can be neglected in comparison to the cross stream diffusion, and for cross stream diffusion and convection to be comparable, okay, cross stream diffusion, convection and the body force term to be comparable in the limit of high Grashof number, it is necessary that delta star into Grashof number per half, okay, is equal to 1, okay, for the boundary layer thickness. This is the relation for the boundary layer thickness. It can be any constant. The solution in terms of the similarity variable will depend on the constant. The solution in terms of the original spatial variables will not in general depend on the constant. Therefore, without loss of generality, I can take delta star is equal to the Grashof number to the minus 1 by 4. Okay. In the limit as the Grashof number becomes large, delta star is equal to Grashof number to the minus 1/4. Okay. With that substitution and neglecting the streamwise diffusion in comparison to the cross stream diffusion, the equation becomes Vx partial Vx by partial x plus Vz partial Vx by partial z is equal to minus partial of the dynamical pressure by partial x plus partial square Vx by partial z plus square, okay, plus T star Gx. Okay. So, this is the momentum conservation equation in the streamwise direction. Okay. Next, we will analyze the momentum conservation equation in the cross stream direction. Okay. Recall that I had written for you the momentum conservation equation in the cross stream direction, okay, rho infinity into V partial Vz by partial x plus Vz, I am sorry, there should be no stars here, these are in dimensional form, V dot grad V, that is Vx partial Vz by partial x plus Vz partial Vz by partial z. Okay. Plus into T star times G z, the component of the gravitational acceleration in the z direction. Okay. Note that the gravitational acceleration is downward. So, at any particular location, the gravitational acceleration will have a component in the cross stream direction and in the streamwise direction as well. Okay. Right at the bottom, the gravitational acceleration is entirely in the cross stream direction, but at any other location, it will have components in the cross stream and the streamwise direction. Okay. So, substitute the scalings. Okay. Vx is scaled by Vc, Vz is scaled by delta times Vc. Okay. Vz is scaled by delta times Vc, Z is scaled by delta times Lc. Okay. So, for the left side you will find that the total scaling is rho infinity Vc square delta by Lc. Okay. Partial Vz plus by partial x plus Vz plus okay. On the right side, pressure is scaled by rho Vc square. Denominator I have delta Lc. Okay. because z is scaled by delta LC. Partial z plus, okay, mu infinity into delta into Vc, because Vz is scaled by delta times Vc, okay, divided by Lc square into partial square Vz plus by partial x star square plus 1 by delta square partial square Vz by partial z plus square, okay, plus rho infinity g beta to T naught minus T infinity T star Gz star. Okay. So that is the equation. Turns out the largest term here is actually this term. Okay, the largest term here is actually this term because it is proportional to 1 over delta. Okay, it's proportional to 1 over delta. Okay. Therefore, I can divide throughout by this largest term, okay, because it's proportional to 1 over delta, and the left side will become delta square into okay. When I divide throughout by this term, I will get mu infinity into Vc by Lc square into delta square, because I have a delta in the numerator here, okay, whereas the pressure term has a delta in the denominator. Okay. So, I will get delta star square, okay, by Grashof number to the half, okay, into partial V z plus by partial x star square plus partial V plus this body force term. Once again, I have scaled it by rho Vc square by delta into Lc. So, I will get a factor of delta star here into T. Okay. This is the momentum conservation equation in the cross stream direction. In the limit, as the Grashof number goes to infinity and delta goes to 0 and delta star is equal to Grashof number to the minus 1 by 4. Okay. You can see that the terms on the left will all cancel out because they are proportional to Grashof number square. Streamwise diffusion of momentum is small compared to cross stream diffusion. In the cross stream diffusion term, this term also is small because it is proportional to 1 over Grashof number to the half, and the body force term is also small. Okay. So, the cross stream momentum conservation equation is just equal to 0 is equal to minus partial P d by partial z plus. Okay. So, that is a cross stream momentum conservation equation. Okay, that the pressure gradient is just equal to 0. And this is a common feature of all boundary layer equations. It turns out that the pressure gradient across the boundary layer will be 0. Okay. Finally, the energy balance equation. Okay. Vx partial t by partial x plus Vz partial t by partial z is equal to alpha infinity partial square t by partial x square plus partial square t by partial z square. Okay. Scaling by the same characteristic velocities that we had, okay, Vx by Vc, x by Lc, z by delta Lc and Vz by delta Vc. Okay. On the left side you will get, okay, Vc into by Lc into Vx star partial t by partial x is equal to alpha infinity, okay, by Lc square into partial square t by partial x square plus 1 by delta square partial square t by partial z, z plus square. And you divide throughout by the prefactor on the left, and I made a mistake here because it should be Vz plus. Okay, I am scaling the velocities by Vz plus and the length by z plus. Okay, so let's kindly correct that. I will get Vx star partial t by partial x I can neglect here the streamwise diffusion in comparison to the cross stream diffusion. Okay. Okay, I can neglect here the streamwise diffusion in comparison to the cross stream diffusion. Okay. Note that this term here was equal to 1 over Prandtl number times Grashof number to the half. Okay. This was the Peclet number, okay, into 1 by delta square. Okay. And we know that this product is 1 because we had defined delta star as Grashof number to the minus 1/4 power. Okay, we had defined delta star as Grashof number to the minus 1/4 power. Okay, so this product is equal to 1, and the equation I get is Vx partial t by partial x plus Vz plus partial t by partial z plus is equal to 1 by Prandtl number partial square t by partial z plus square, where I have neglected streamwise diffusion of heat in comparison to cross stream diffusion. Okay. So, these are the equations that I get: the mass conservation equation, the momentum conservation equation in the streamwise direction and the cross stream direction, and the energy conservation equation. In all cases, we neglect the streamwise diffusion comparison to cross stream diffusion, and the momentum conservation equation perpendicular to the surface in the cross stream direction just reduces to 0 pressure gradient in that direction. So, these are the scaled equations, and the boundary layer thickness is proportional to Grashof number to the minus 1/4. So, based on these equations and the boundary layer thickness, we will discuss the form of the correlation for the Nusselt number. That I will continue in the next lecture. I will see you then.